All right, so we talked about conformations of ethane, rotation around sigma bonds. Now, of course, as our molecules get more complicated, the conformations get more complicated too. Let's look at butane, and this is problem whatever it is on your quiz, maybe 2. Butane looks like this. And we're going to focus on the conformation between, about the bond between 2 and 3. The bond between 1 and 2 is going to be boring. It's just going to be a staggered conformation that looks like this, only carbon 2 in the back, one of these groups needs to be a carbon. For the conformation between 2 and 3, though, we've got some interesting things going on. So imagine, put yourself in the plane of the page and look down the bond between 2 and 3. And as we're doing this, the methyl group, that is carbon 1, should be, it's in the plane of the page here, it should be pointing straight down in our Newman projection view. Then the proton that's a wedge should be coming upwards and out and to our right. The proton that's a dash on carbon 2 should be coming upwards and to our left. Then remember, carbon 3 is in the back. We can't see it, but we can see the things that are bonded to it. From this perspective, you tell me, where should I put the methyl group? Straight up, right? Methyl group on carbon 4 should be straight up. Good. The methyl group that is carbon 4. And then the wedge proton on carbon 3 should be pointing downwards to our right, and the dash proton on carbon 3 should be pointing downwards to our left. We're going to focus, this is a staggered conformation because all the groups in the front are staggered in between all the groups in the back. What's the relationship between the methyl group in the front and the methyl group in the back? What's the right word to describe that relationship? Anti. Yep, they're anti to each other, or anti is fine too, opposite. Opposite each other. Now let's imagine that we rotate the carbon in the front, and let's imagine we rotate by what's going to look like 120 degrees counterclockwise. So we're going to rotate about the C2, C3 bond. That will take the methyl group here and it's going to swing it this way such that the methyl group, which is anti, the purple methyl group, which is anti to the blue methyl group in the back, should now be in a different place. So I'm going to draw the carbon in the back. I'm going to draw the 3 positions that for carbon 2 in the front. I want you to fill in where the purple methyl group should be if I rotate around that bond and I take this methyl group and swing it upwards.
Is that 180 degrees or
120. Yep. So where is the purple methyl group going to be? Where do you think?
on the right?
On the right and pointing upward. Yeah. And then the other 2 positions are going to be protons. This is us doing one ka-chunk. We're going to go through an eclipsed conformation and then move the methyl group, rotating it from here to there. Okay? Now what is the, erasing instead of highlighting. Now what is the relationship between the purple and blue methyl groups? What's the right word? Gauche. You can pronounce it gauchy if you want to, but I think gauche sounds fancier. Any French speakers out there? Gauche is a French word. What's it mean?
Left.
To the left. It's ironic that it's on the right here, but we're not using it in any left and right sense. We just mean side by side. Okay. So when someone's trying to insult me in a fancy sounding way and say, "Oh, that's so gauche," what do they mean? I think that's a fancy way of saying lame, but, oh, out in left field, okay. Yeah. Well, if you're going to insult me, you got to use words I understand. Otherwise, it just rolls off. So, okay. Good. Now, on the way to this second staggered conformation, along the way, there was what I will call a transition state, a high energy conformation that was in between these two staggered conformations. Let's draw what that would have looked like. So again, I'm going to draw my circle. Again, I'm going to draw the blue methyl group in the back pointing upward like this. We're going to draw our carbon 2 here. This is our carbon 4. What would that high energy transition state have looked like? The one that's in between this staggered conformation on the left and this one on the right. The hydrogen lined up with what? So this hydrogen here should be lined up, maybe we'll call it the orange hydrogen, should now be eclipsed with and lined up with the methyl group in the back. Okay. What about the purple methyl group? Where should it be? Yeah, it should be bottom right, lined up with that hydrogen. And then another hydrogen here. So this is an eclipsed conformation. Good. Of these two conformations, these two staggered conformations, which do you think is better or more stable? Which one minimizes steric repulsion or electron-electron repulsion? You guys are pointing that direction, but I think that means that direction for me. So the anti one, yes. The anti one is more stable, and the reason is it minimizes steric repulsion. And by steric repulsion, we mean repulsion between the electrons in surrounding the methyl groups. Let me show you what this looks like. In Spartan, I'll draw butane, and we'll show you the space-filling view of butane. And then we're going to show you a different conformation. So looking down the bond between the carbon C2 and C3, this is a gauche conformation. The methyl group in the front, the C1 methyl group in the front, is gauche to the C4 methyl group in the back. This is an anti-conformation. They're now anti to each other. If you look at the space-filling models of those, you can see that in the gauche conformation, the two methyl groups on either side are now bumping into each other and touching. So having interactions between two methyl groups that are gauche to each other, that's repulsive, meaning not that it's disgusting or gross, but it's higher in energy. And you can see by how much it's high. There's an energy diagram on the left over here. The anti-conformation is lower than the gauche conformation by about 3 kilocalories per mole, which is a sizable amount. Okay? So you would expect there to be more of this anti-conformation than this gauche conformation at any point in solution. All right, there's so much more we could say about that, but I think that gives you enough to work on one of the problems in your problem set, which is going to have you do a molecule. It's not going to be butane, it's going to be something else, but it's going to have you look down a bond in this molecule and draw the various staggered conformations and then decide which one is best. And the one that's best is the one that keeps the larger things on either carbon, front and back, as anti to each other as possible. All right, any questions about that one? Okay. I think next on your quiz is a question about drawing a chair conformation for a 6-membered ring. Is that right? Yeah? Okay. Let's talk about that. So there are a lot of 6-membered rings in biology. We draw them the Lewis structure like this. And of course, you can fill in the hydrogens that are implied but not shown. And if you wanted to, you could draw in all the carbons. Unfortunately, this drawing, though it gives you all the right connectivity, misses something. And that is, it misses the way the molecule actually looks in solution. If all of these carbon-carbon bonds are in the plane of the page, that makes this a perfect hexagon, right? Anybody know from geometry what the inside angle for a perfect hexagon is? Don't worry, it's fine if you don't know. It's 120 degrees. Now, tell me, is that, for a perfect hexagon, is that 120 degrees equal to the bond angles you would prefer for sp3 hybridization? What's the preferred bond angle? It's tetrahedral, right? The preferred bond angle is 109. So if we're saying that this molecule has to be totally flat, like I've drawn it here, we're forcing the molecule to adopt bond angles that are not consistent with what it would prefer to do. That introduces something called strain. Anytime you force a molecule to do something that's unfavorable, that's called strain. The steric repulsion in the gauche conformation is an example of strain. The gauche conformation is less stable than the anti-conformation because of the repulsion or strain present there. Similarly, if you force an sp3 hybridized carbon to have 120 degree bond angles, that introduces some strain as well. So what actually happens is the molecule adjusts its shape. It relaxes. We call it puckering. That doesn't make a lot of sense, but that's what organic chemists call it. Ring puckering to minimize strain. And what happens in the ring puckering of a cyclohexane ring is that these 3 carbons here will move out of the plane of the page slightly. Okay. Let me just highlight that. The 3 carbons here move up, out of the page slightly. And the other 3 carbons, the blue ones, are going to move down into the page slightly. And you will see that that immediately relieves the ring strain. It's very difficult to draw this from an overhead view, so instead we're going to learn to draw it from a side-by-side view. And we'll do this first looking in the program Spartan so you can see how it works. So I'm going to just trash everything there. Here is a 6-membered ring. Okay, cyclohexane. Notice from our perspective there, all the CC bonds are in the plane of the page. Here is our perspective of what the molecule actually looks like. You can see the carbon at the top. I don't have a, I need a pointer. Where is the pointer? No, it's not going to help. The carbon at the top, if we start numbering clockwise, 1, 2, 3, 4, 5, 6 around the ring, carbons at 1, 3, and 5, you can see are slightly above where carbons 2, 4, and 6 are. Okay, 1, 3, and 5 have come back out towards you a little bit, and 2, 3, and 5. 1, 3, and 5 have come out towards you a little bit. 2, 4, and 6 have been pushed away into the page a little bit. And this shape relieves the ring strain. If I go and look and measure the bond angles in this shape of the molecule, they are all now 109.5. They're right where they should be. Now, there's some interesting things about this shape. First, it's called a chair. This is the chair conformation for cyclohexane. Where did that come from? It looks nothing like a chair. Well, okay. Do you guys know, you ever heard or seen an Adirondack chair? It's kind of, you can Google it. It kind of has a back and then a seat and then a place to put your feet. These are the armrests. That is a chair. Yeah. Well, if you look at that from, look at this cyclohexane ring from that perspective, the methyl group at the top is the back of the chair. The CH2 at the top is the back of the chair. The 4 CH2s there in the middle are where you would sit, and then the CH2 at the bottom is where your feet go. That's why it's called a chair. You don't actually, just Google it and you'll see somebody will explain it to you. It's not that big of a deal, but this conformation for a 6-membered ring is called a chair. You'll notice as we look at that on the carbons that are up, we'll call, as I said, carbons 1, 3, and 5, they're up relative to the other ones. Carbons 2, 4, and 6 are down. Notice that the up carbons, 1, 3, and 5, have CH bonds that point directly upwards. And notice that the down carbons on 2, 4, and 6 have CH bonds that point directly downwards. Up carbons have directly up pointing CH groups. Down carbons have directly down pointing CH groups. Now, let me be precise. Each carbon, up or down, has 2 kinds of protons, has 2 different protons. What I'm saying is for the up carbons, there are protons that point directly up. Those are called axial protons, okay? The up carbons 1, 3, and 5 have protons, axial protons that are pointing up. The down carbons 2, 4, and 6 have axial protons pointing down. Now, there are other protons on those carbons that are splayed outward. If we rotate the ring around like this, like we might rotate a globe, the axial protons point to the North Pole and the South Pole respectively, and the other protons are splayed outward along the equator, and we call those equatorial protons. So in a cyclohexane ring, carbons 1, 3, and 5 have axial protons pointing upward, and then what direction do the equatorial protons point on carbons 1, 3, and 5? Sort of angled downwards towards the bottom half of the ring. They're not pointing directly downwards, they're splayed, but if you drew a midpoint line around a sphere that represented the globe that is this cyclohexane ring, the axial up protons point towards the North Pole, the equatorial down protons point just a little bit south of the equator. Losing you, or are you sort of okay? Sort of okay. In contrast, on the down carbons, the axial protons point downward towards the South Pole, and the equatorial up protons are splayed upward a little bit north of the equator. Now, there's a ton that we could do here. We don't want to overdo it, but you want to know enough about it so that you can draw a chair and think sensibly about it. So, let me show you how to draw this conformation of a cyclohexane ring. Start with a line that you're going to angle downward a little bit to the left. Turns out you can do this towards the right, but this is what we're going to do. Okay, then another line angled only slightly downward to the right, and then another line angled slightly upward to the right. So those are the 3 lines that you need. We're going to draw a third line here, and we're going to draw it so that it's parallel to this one. This is why I'm saying once you've got the first 3 lines, you're good to go on drawing a chair. Draw a line here that is parallel to this one. Then here, we're going to draw a line that's parallel to this one. And then we'll complete the chair by drawing a line here that's parallel to that one. So let's just highlight that. The blue lines are parallel to each other. The orange lines are parallel to each other. And the pink lines are parallel to each other. It looks like a stylized bow tie. And if you tilt it upward kind of like this and squint your eyes and imagine it a little bit, it sort of looks like an Adirondack chair. Okay. Now, from our perspective here, carbons 1, 3, and 5 are pointing upward. Whereas, and we're viewing this ring from the side, whereas carbons 4, that's not 4, gosh, 2, 4, and 6 are pointing downward. So here's how you draw the hydrogens on the cyclohexane ring. Up carbons 1, 3, and 5 are going to have axial up protons. And the way we draw that is just a straight line up on carbon 3, carbon 1, and carbon 5. Down carbons 2, 4, and 6, we're going to draw axial down hydrogens, and we're going to do that just with a straight line down on carbon 4 and carbon 6 and carbon 2, and I'm using the sort of broken line to indicate that it's back behind. Questions about how to draw the axial hydrogens? Yeah.
Just to clarify, it's the corners that are the carbon still.
Right. Every time the lines meet, this is a skeletal structure. Every time the lines meet, those are carbons. Yep. Vertices are carbons. Okay. Now the hard part is drawing the equatorial hydrogens. A couple of things that'll help. If you're trying to draw an equatorial hydrogen on a carbon that already has an up axial hydrogen, your equatorial hydrogen needs to be splayed downwards. And the best way to do that is to see, for example, on carbon 1, I need to draw a line here that is parallel to the other orange lines in my chair. The axial down position on carbon 1 here should be parallel to the orange lines. Similarly, the equatorial down proton on carbon 5 should be parallel to the blue lines. From our perspective, it's angled down slightly below the equator, and then equatorial down proton for carbon 3 needs to be parallel to the pink lines. All right. So I'll just circle my axial up protons on 1, 3, and 5, and my equatorial down protons, I'll put a triangle around. Those are the equatorial protons on 1, 3, and 5. How about on carbon 4? If I want to draw an equatorial, carbon 4 is a down carbon. It has axial down hydrogens, but it should also have an equatorial up hydrogen. On carbon 4, how should I draw an equatorial up hydrogen? What line do I want it to be parallel to?
Yellowish.
Yeah, orange or yellow. Good. Whatever color that is. Okay. How about on carbon 6? What line should the up equatorial hydrogen be parallel to? Pink. Good. And then this one's a little tricky. On carbon 2, I should draw an up equatorial hydrogen that's parallel to what? Blue. And that one is just going to be in this direction. I have to remember that it's equatorial and it's angled slightly upwards. Okay. So that's how to draw a 6-membered ring or a chair conformation of cyclohexane. Now, why do we do this? And the answer is you're seeing that on each carbon there can be distinct environments. On each carbon you've got an axial environment and an equatorial environment, and those environments are different. Do you see how the the triangle equatorial proton isn't very close? Pink triangle equatorial proton is not very close to blue triangle equatorial proton. They're quite far away. Whereas the axial circle proton on carbon 3 is quite close to the axial circle proton on carbon 5. The environments are different. Equatorial environments are fairly unhindered, minimal steric repulsion. You will see that axial environments have more steric repulsion. Okay, so as an example, let's look at this structure for methyl cyclohexane, and this is what your quiz asks you to do. Let's say that the methyl group is at carbon 1, and let's draw our chair in the same way that we've done it. So I'm going to draw the chair for you and number the carbons, and I want you to fill in all the hydrogens and the methyl group where they ought to be. Noticing that the methyl group here on carbon 1 is pointing up towards us. So from our side view in the chair conformation, that methyl group should be pointing up towards the top of the page or angled towards the top of the page, depending on whether it's axial or equatorial. If you're concerned about drawing chairs that are pretty, don't worry, practice it until it gets intelligible. There's not going to be any points on an exam for drawing a pretty chair because my exams are multiple choice. But if you can't draw a chair that you can interpret and that makes sense, it might be difficult for you to select the correct answer. So you want your chairs to be decent, but you don't want to spend forever. questions in the exams? Normally 20, 25-ish. Yeah. I mean, they're multiple choice. Yeah, there's, question one, parts A through Z, and then, usually one, you've got to select. Yeah, I'll tell you more about that.
I'll tell you more about that in 2 days.
2 days, yeah. Don't want to grab the cover before then. Okay, how are you doing on your chair?
It looks wonderful.
As long as you have you're free to represent that methyl group as just a skeletal structure, just a stick. If you want to write it as CH3, or if you want to write out the CH bonds on the methyl group, how you think they would be, that's fine. I'm mostly concerned about you getting the methyl group in the right spot, whether it's axial or equatorial. All right, you had a minute to figure it out. Which on carbon 1, which is an up carbon, my methyl group is up. So which position is that? Axial or equatorial on carbon 1? Axial. So you draw CH3 here, and then where am I going to draw the CH bond on carbon 1? All right, now this is how you discern, this is where we separate the chair drawing sheep from the chair non-drawing goats or something like that. Like some people will draw an equatorial hydrogen going like that. That's a problem because it captures the idea of equatorial, but it makes me think that you think that proton is pointing up, and it can't be because it's pointing down here and the methyl group's pointing up here. So again, if you're on carbon 1, you want to draw the equatorial hydrogen parallel to the bond between 2 and 3. In other words, I want it to be here. Okay, good. And then you could draw the rest of the hydrogens by analogy to what's there. I'll draw the other ones here, and then the equatorial hydrogens like that. Okay, good. Now, here's something you don't want to know. In the same way that butane, maybe you do want to know. I shouldn't assume you don't want to know. I always assume another end of semester comment is it's like drinking from a fire hose. And so I always assume that that students wish I wouldn't tell them things, but perhaps you're curious, so I won't make that assumption anymore. As I'm sure you're dying to know, just as in butane you can rotate around carbon-carbon bonds to access a different conformation, you can do that with chairs as well. No, okay? So imagine a conformation, and it's not going to be that bad. Imagine a conformation. Do you remember how I told you that carbons 1, 3, and 5 are sort of pointing up, and carbons 2, 4, and 6 are sort of angled down into the page? Imagine that we switch that. Imagine that the blue carbons 2, 4, and 6 now tip up out of the plane of the page, and carbons 1, 3, and 5 now poke down into the plane of the page. Yeah? Yes, so that kind of thing is called chair flipping. That's a misnomer because it doesn't mean that you're taking the chair like a pancake and flipping it over. It means we're swapping which carbons are up and which carbons are down. That's really hard to represent from the side, and some people do it better than others. I'm just going to continue drawing the chair the same way. Only I'm going to say now that carbons 1, 3, and 5, which used to be at up positions, must now be at down positions. And carbons 2, 4, and 6, which used to be at down positions, are now at up positions. So that's literally the switch that's going on here. 2, 4, and 6 are coming out of the plane of the page, pointing up towards us, and now 1, 3, and 5 are going down into the page. Yeah? You could have drawn this the same way by putting, if you wanted to draw 1 here. Yeah. Yep. Okay, so now let's see how that changes things. On carbon 1, the up group is the methyl group, and the up position used to be axial. Now that carbon 1 is at a down position, where should the methyl group be? Should be equatorial and angled upward, so that's going to be here. Again, I'm going to choose to put my methyl group parallel to the bond between 2 and 3, or the bond between 5 and 6. Okay? The methyl group should be equatorial. Now how about the proton on carbon 1, the down proton that used to be equatorial? What should it be? Axial. Axial down. Good. So this is called, this conformational equilibrium, this change between two conformations, is called ring flipping, but again, that's sort of a misnomer. It just means the up carbons push downward and the down carbons push upward and trade places. But this is called ring flipping. And as you can see, the two conformations are not identical. In one of them, the methyl is in an axial environment. In the other, the methyl is in an equatorial environment. Based on what I told you before, which of these things do you think is more unstable? Axial. Yeah, this is the less stable conformation. And the reason it's less stable is because I'm going to highlight the axial methyl group and the other two axial groups. And you're going to see, if we go back to Spartan, you're going to see that methyl group actually starts bumping into the other axial protons on carbons 3 and 5. And that is steric repulsion. So going to Spartan, I need to add a methyl group onto my cyclohexane. There. And there you can see, here is the conformation where the methyl group on carbon 1 is equatorial. Here is the conformation where the methyl group on carbon 1 is axial. Now in that picture, it doesn't immediately look like the CH bonds on the methyl group on carbon 1 are bumping into the CH bonds on axial protons that are on carbons 1 and 3. But if you make it space filling, oops, that was not what I had planned. If you make it space filling, you can see, we'll go from space filling back to ball and stick, back to space filling. So the methyl group is bumping into those other axial protons. In fact, if you're paying really close attention, you can see that to avoid bumping into it, that methyl group is not perfectly axial. It's, here's our second time we're going to say it, leaning a little bit to the side, okay? Leaning away because of steric repulsion. So having groups axial is less stable than having groups equatorial. To summarize, notice that when we ring flip, groups that are up stay up, groups that are down stay down, but axial and equatorial switch. The methyl group used to be up axial. Now, after the ring flip, it is up equatorial. And as I said, this is the axial conformation is the more stable one. All right, there's a lot more we could do there, but that's enough to be getting started, especially when we start to draw carbohydrates, many of which form six-membered rings. You're going to want to be able to know the difference between an axial versus equatorial group. Okay, next time we're going to talk about alkenes, and I brought my bag of fats and oils, so we'll be talking about what's in peanut butter and Crisco and coconut oil. I'm not going to be giving out taste samples though, because I have no idea. It's been years for the stuff in the bag. I don't know how old it is. Might not be healthy. All right, see you next time.